All right, so this is section 4.5, inequalities involving quadratic functions. Don't really like that name, inequalities involving quadratic functions. So I personally renamed it, this section, to solving quadratic inequalities. In other words, there's no quadratic function involved in this discussion unless we bring it in the discussion. So we want to solve quadratic inequalities, probably using a quadratic function to do it, but that's a choice not really tied to the questions that we're solving themselves. So to punctuate that, this is what I mean. To solve the inequality, ax squared plus bx plus c is greater than 0. So that's what we want to do, solve the inequality. One option is to graph the quadratic function that has the same a, b, and c, and then observe which quadrants it's in. Basically, if f of x is greater than 0, that would mean it's in quadrant 1 or quadrant 2. And if where the graph occupies quadrant 1 or quadrant 2, f of x is positive, or the quadratic function is positive. When they're talking about less than, they're talking about f of x being less than 0, and that's quadrants 3 and quadrant 4. So let's go through it. All right, so we want to solve, again, the instructions are clear, the question's clear. This is a quadratic inequality. And to solve it, we're going to, or the author is going to, do a little too much work, in my opinion, but the author's going to graph the parabola. So it was the author's choice to take this and rewrite it as essentially y equals this, x squared minus 2x minus 15. That's fine. Just understand it's a choice. So I'm sorry, the author's doing just a lot of extra work here, but found the vertex is negative 15. The y-intercept is negative 15. Set the function equal to 0. Found the x-intercepts to be negative 3 and 5. I already have more of the information than I need to know that the graph is going to have to go like this, because remember, I knew the lead coefficient was 1, which is a positive number. And so since I knew that, I knew the graph was going to, where the graph was going to be above the x-axis and where it's going to be below the x-axis. Well, let's keep going with the author's presentation. The author even took the extra time to find the vertex to get a really accurate image. Again, you don't need all of this, but that's fine. We know we can do it. All right, let's get to the final answer. All right, remember what the question was. It was asking, when was the function less than 0? And less than or equal to 0. And it's equal to 0 at negative 3, it's equal to 0 at 5, and it's less than 0 on this entire region. So just this piece of the number line is what we want to just clip. Just get that. And that would be the solution. They tried it again. Here's an inequality. We can put the inequality in standard form, solving it. And if we call this f of x and graph it, we're looking for when the function again is below the x-axis. So finding things like the intercepts and even the vertex. Gives us plenty of information. And again, the question was, when is this thing less than 0? This time it was less than 0, so I will not include the endpoints. It's just the value between 2 and 3. I really like this question because it's asking, it gives you this parabola, which you may or may not have drawn. So I don't want to assume that you have this beautiful picture when you're doing this problem. They give you a parabola and a line, and basically you want to know, when is the parabola underneath the line? So when is the parabola, which is down here, underneath the line, which is up here? And you can see from the picture, it's going to be from -2 to 3. So it's going to be in this, or I guess, region right here, or interval right here. I can only assume that the other didn't assume that you had this beautiful picture drawn. In other words, how would you know exactly where this goes unless you had every point accurately? Would you know exactly what this picture looks like? So basically, we just want to solve this. When is f of x less than g of x? And I'll just go ahead and substitute in here, which is what the author does in the next slide. F of x less than g of x. I get x squared minus x minus 6 is less than 0. Not less than or equal to 0. It said less than. So this is what I want to solve in order to solve this. Again, those of us who've already graphed this have done this problem and moved on to the next, but now the author's saying, let's figure out what function we're dealing with, solve that in as long a way as possible, and use that for our answer. All right. But actually, the author did do a little bit more here. I'm not, again, the only reason why the author would do this. So we know that x, when x is -2, both of the functions, f of x and g of x, will be equal. So if I just used f of x, remember f of x was x squared. If I put -2 in here, I'd get 4. If I put 3 in there, I'd get 9. And so that's what these points are. So the author's still kind of holding on to the idea that, maybe it wouldn't be such a bad idea to graph this thing and even be aware of the points where they meet. Not required to answer the question, but the author does seem to like to do a lot of graphing on these problems. So he graphs the whole thing and comes to the conclusion that the parabola is less than the line on that interval from -2 to 3. All right, well, this particular problem doesn't have any x-intercepts, and I guess it helps to graph it. When you graph it, you can see it's always greater than 0. So the entire number line. But so I just wrote this here because I want to do a problem a little faster, right? So this was the first example. I factored it. There really isn't anything I can do with this. Like I can't go step. Anything I could write down underneath this, like x plus 3 is less than or equal to 0, because that isn't really necessarily true. There is no property if two things multiply and they're less than 0 that we know which one's less than 0 or something like that. In other words, there's a property that would let us continue if that were an equal sign. But if it's not an equal sign, what we're going to do is we're going to factor it, get factored side, 0 side, and this critical number, the number when I set this equal to 0, would be -3, and this one would be 0 at +5. And we still want to know when is this pair, this product, less than 0. Now, you could tell yourself, well, this does look like a parabola, concave up, so it's less than 0 between the points, and it's equal to 0 here and here. And hopefully you see what I'm doing. I'm not doing any more analysis than I need to know for sure when it's equal to 0 and when it's negative. Now, we could even do this if this weren't graphing. So let me do another problem. Let me just say, what if I had factored side and it was x plus 3, x minus 1, and x minus 6 is less than 0. So this problem, I really can't rely on the graph at all. But I can plot the critical points. And the reason why I say I can't rely on the graph is we know parabolas, but I don't know what's supposed to happen here as far as the graph snaking through those points. So I just want to completely separate this and do a very non-graphing technique. All right, so the question is, when, and it will be more than one interval, when is this less than 0? And by the way, I'm previewing a topic that gets touched on in chapter 5, but I think now's a good time to do it. All right, so I found my critical points, and I'm going to test a point in each interval. So if I test a point here, this interval is from 6 to infinity. And if I pick a point like 10, I would get 13 times 9 times 4. The numbers aren't important, but the signs are. Notice I get positive times positive times positive. And so I picked 10 as the representative number, but the point is it's always going to be the same sign in this entire interval. Now, in this next interval, it will most likely change signs. I say most likely because there are exceptions, so we'll take a test point in this interval. So in this interval, the interval from 1 to 6, let's pick a number. Let's pick a number right in between 1 and 7. Well, right in between 1 and 6, but let's pick 3. All right, so if I pick 3, I'm going to get 6 times 2 times negative 3. So notice it's positive, positive, negative. Now that would have been true if I had picked 2. I would have also got positive, positive, negative. You know, that's the whole point. Any number in here would make this one positive, and this one negative. With one negative, it's negative. Test a point between negative 3 and 0. Probably the easiest point would be 0. Sorry, negative 3 and positive 1. Easiest test point might be 0. 3, negative 1, negative 6. 2 negatives. Exactly 2 negatives means positive. And we could test the last one, but the point is, I'm not really getting a graphing. As a matter of fact, this is almost a graphing technique that we'll use later. But I know when the graph is negative. Here, it's negative, and here, it's negative. So putting those together, the solution is negative infinity, negative 3, union 1, 6. So this is the question, this was the solution, and there was no function involved. I never tried to draw the graph. Now, if I did want to draw this graph, in other words, if I wanted to multiply it out as a polynomial and draw the function itself, I actually have a lot more information than I did before. I know the graph is negative in this interval between these two values. I know the graph is positive between these values, meaning it would be in these quadrants. And I know it's negative afterwards. So I kind of have a rough idea of what the graph would look like, but we haven't graphed things like this yet. So there is a connection between what we're doing now, using graphs to solve inequalities, and then kind of the reverse of that, using inequalities to draw graphs. So just wanted to throw that little foreshadowing out there for our next chapter. But this is section 4.5, and that's certainly enough of section 4.5.